Reality isn't what you think it is. Every moment of your life, you assume the world exists independently, waiting to be discovered. You believe your eyes see truth, your mind grasps facts, your knowledge builds on certainty. But in 1927, a young German physicist named Werner Heisenberg shattered that illusion forever. He proved something so disturbing, so fundamentally unsettling, that even Albert Einstein refused to accept it. Heisenberg showed that the universe doesn't just hide its secrets. It makes certain truths absolutely, fundamentally, impossibly unknowable. Not because our instruments aren't good enough, not because we haven't tried hard enough, but because reality itself forbids it. This is the story of how one equation destroyed the foundation of human knowledge and forced us to confront a terrifying question. If we can never truly know anything with absolute certainty, what does that mean for truth, for science, for the very fabric of existence? What Heisenberg discovered wasn't just a problem with measurement. It was a revelation about the nature of consciousness, observation, and the mysterious relationship between the mind and the universe it inhabits. Before we dive into the abyss that Heisenberg opened, we need to understand the world he destroyed. For 2 centuries, humanity had enjoyed the comfort of scientific certainty. Isaac Newton's laws of motion, published in 1687, had transformed the cosmos into a magnificent clockwork mechanism. Every planet, every star, every falling apple obeyed precise mathematical rules. The universe became predictable, knowable, conquerable. Scientists developed an intoxicating belief called determinism. The idea was beautifully simple and terrifyingly absolute. If you could know the exact position and velocity of every particle in the universe at any given moment, you could predict the entire future and reconstruct the entire past. Nothing would be uncertain, nothing would be random, nothing would be free. The future was already written in the present configuration of atoms. Pierre-Simon Laplace articulated this vision through his famous thought experiment of a superintelligent being, later called Laplace's demon, who could observe all of nature and for whom nothing would be uncertain. The future as well as the past would be present to its eyes. This wasn't just physics, it was philosophy with profound implications for human existence. If the universe was deterministic, then free will was an illusion. Your choices, your thoughts, your decisions, all of them were predetermined by the initial conditions of the Big Bang, rippling forward through cause and effect, like dominoes falling in slow motion across billions of years. You weren't free. You were a biological machine, executing a program written 13.8 billion years ago. Everything you've ever done, everything you will do, was inevitable. Religious implications were staggering. Calvinist predestination, the idea that salvation was predetermined before birth, aligned perfectly with this deterministic worldview. Ethics, morality, responsibility, all became questionable in a universe where choice was impossible. Scientists and philosophers wrestled with this uncomfortable conclusion, but the mathematics was undeniable. The clockwork universe ticked forward with mechanical precision, and humanity was just another gear in the machine. Then quantum mechanics arrived, and everything changed. In the early 20th century, physicists probing the subatomic world discovered something deeply strange. Light behaved sometimes as a wave, sometimes as a particle. Electrons appeared in one place, then another, without traveling the space between. Energy didn't flow smoothly, but came in discrete packets called quanta. The reliable, predictable world of Newton was collapsing at its foundations. Werner Heisenberg, born in 1901 in Würzburg, Germany, was brilliant, ambitious, and intensely philosophical. He studied under Niels Bohr and Max Born, working at the cutting edge of this strange new physics. In 1926 and 27, while still in his 20s, Heisenberg made the discovery that would haunt physics forever. He was trying to understand how we measure quantum particles, how we observe the fundamental building blocks of reality. What he found was that observation itself was the problem. Imagine trying to see an electron. To see something, you need light. Light bounces off the object and enters your eye. But here's the problem. Light carries energy and momentum. When a photon hits an electron to reveal its position, it kicks the electron, changing its velocity. The more precisely you measure where the electron is, using higher energy photons to get better resolution, the more you disturb its momentum. Conversely, if you try to measure its momentum precisely, you lose information about its position. This wasn't a technological limitation. This was fundamental to nature. Heisenberg formalized this with an equation that would become legendary, the uncertainty principle. Mathematically, it states that the product of the uncertainties in position and momentum must be greater than or equal to a tiny number. Planck's constant divided by 4 pi. In simpler terms, the more you know about where something is, the less you can know about where it's going, and vice versa. Certain pairs of properties, called complementary variables, cannot be simultaneously known with arbitrary precision. This principle applies to other pairs too: energy and time, angular momentum and angular position. The universe enforces these limits not because of bad equipment, but because of the fundamental structure of quantum mechanics. Nature draws a line and says, beyond this, you cannot know. The implications were staggering. In the classical world, you could theoretically measure everything about a particle and predict its future path perfectly. In the quantum world, that dream died. Uncertainty wasn't ignorance, it was built into the fabric of reality. But Heisenberg's discovery went deeper than measurement problems. It challenged the very concept of objective reality. In classical physics, we assume objects have definite properties, whether we measure them or not. A baseball has a specific position and velocity, even when nobody's looking. It exists independently, waiting to be observed. Quantum mechanics, through Heisenberg's principle, suggested something radically different. Particles don't have definite properties until they're measured. Before observation, an electron doesn't have a position and momentum that we simply don't know. It literally doesn't have those properties at all. It exists in what physicists call superposition, a ghostly state of all possibilities at once, until measurement forces it to choose. This is where things get philosophically disturbing. If properties don't exist until observation, then what role does the observer play? Does consciousness create reality? Heisenberg himself, influenced by philosophers like Immanuel Kant, argued that we can never know the objective world in itself, only our interaction with it. The act of measurement doesn't reveal pre-existing reality. It participates in creating what we observe. Reality isn't independent of observation. It's fundamentally entangled with it. The famous double-slit experiment illustrates this weirdness perfectly. Fire electrons, one at a time, through 2 slits toward a detector screen. When you don't measure which slit the electron passes through, it behaves like a wave, creating an interference pattern, as if it went through both slits simultaneously. But the moment you place a detector to observe which slit it uses, the interference pattern vanishes. The electron behaves like a particle, going through one slit or the other. The act of observation changes the outcome. It's as if the electron knows it's being watched and adjusts its behavior accordingly. This led to one of the most controversial and misunderstood ideas in physics, the observer effect. Some interpretations suggested that conscious observation collapses the quantum wave function, forcing probability into actuality. Physicist Eugene Wigner even proposed that consciousness itself was necessary for quantum measurements, that the mind was the boundary between the quantum and classical worlds. In his thought experiment, Wigner's Friend, he explored what happens when one observer measures a quantum system and another observer observes the first observer. The question became, at what point does reality become definite? When the instrument detects it, when a human reads the instrument, when a conscious mind comprehends it. Most modern physicists reject the idea that consciousness is special or necessary for quantum measurements. Experiments have shown that any interaction, whether with a detector, an air molecule, or a chunk of metal, can collapse the wave function through a process called decay. The environment constantly measures quantum systems, entangling them with countless particles and effectively choosing states without any minds involved. Consciousness, despite its subjective importance to us, appears to play no privileged role in quantum mechanics. But even without mystical, consciousness-based interpretations, the uncertainty principle still demolishes our intuitive understanding of knowledge. It tells us there are fundamental limits to what can be known, not because of human inadequacy, but because of nature's design. You cannot outsmart the uncertainty principle with better technology. You cannot bypass it with clever techniques. You cannot reduce it to zero no matter how hard you try. These limits are absolute, enforced by the mathematical structure of quantum theory and confirmed by countless experiments. The philosophical implications explode in every direction. Epistemology, the study of knowledge, has to confront the fact that perfect knowledge is impossible. Science, which seeks to understand and predict the natural world, must accept inherent unpredictability at its foundation. The scientific method assumes we can observe, measure, theorize, and test hypotheses to reveal truth. But if observation itself changes what we're observing, and if certain truths are fundamentally hidden, then what does science really tell us? Perhaps, as Heisenberg believed, science doesn't describe objective reality, but only our relationship with reality, our methods of interaction, our patterns of measurement. This touches on deeper metaphysical questions about the nature of existence. Does reality exist independently of observation? The uncertainty principle doesn't answer this definitively, but it forces us to question assumptions we took for granted. Some interpretations, like the Copenhagen interpretation championed by Niels Bohr and Heisenberg, suggest that it's meaningless to ask what a particle is doing when we're not observing it. Properties like position and momentum don't exist in the absence of measurement. Other interpretations, like Bohmian mechanics, propose hidden variables and deterministic laws beneath the quantum fog, preserving objective reality at the cost of introducing non-local, faster-than-light influences. The debate between determinism and indeterminism intensified after Heisenberg. Einstein famously declared that God does not play dice with the universe, insisting that quantum mechanics must be incomplete, that there must be deeper deterministic laws we haven't discovered yet. Heisenberg and Bohr disagreed, arguing that quantum mechanics is complete, and that nature is fundamentally probabilistic. This wasn't just a scientific dispute. It was a philosophical battleground over the very nature of causality, randomness, and reality. Here's the crucial point that many people miss. Heisenberg's uncertainty principle doesn't just introduce randomness. It introduces a specific kind of uncertainty that challenges determinism in a unique way. In classical physics, randomness could exist due to ignorance. You don't know the initial conditions well enough, so outcomes seem random. But quantum uncertainty is different. It's not epistemic uncertainty about hidden facts. It's ontic uncertainty, uncertainty built into the nature of things themselves. Particles genuinely don't have simultaneous, precise positions and momenta to know. This suggests the universe might be fundamentally indeterministic at its core. If the universe is indeterministic, then the rigid determinism that threatened free will collapses. Some philosophers saw Heisenberg's principle as a possible rescue for human freedom. If quantum events are genuinely random and not predetermined, and if those random events could influence brain processes, then maybe our choices aren't locked into deterministic chains. Maybe there's space for agency, for genuine novelty, for freedom. Arthur Holly Compton championed this idea, suggesting quantum indeterminacy could be amplified to the macroscopic level, providing a basis for free will. But this rescue comes with complications. Does randomness really grant freedom? If your decisions are influenced by random quantum fluctuations, are they truly yours? Randomness doesn't feel like freedom. It feels like chance, like throwing dice. True freedom seems to require control, not randomness. Philosophers have struggled with this for decades. Compatibilists argue that free will is compatible with determinism, that freedom means acting according to your desires and intentions, even if those desires are ultimately caused. Incompatibilists insist that genuine freedom requires indeterminism, but they face the problem of explaining how randomness translates into meaningful agency. Heisenberg himself was deeply philosophical about these issues. He saw the uncertainty principle, not just as physics, but as a statement about the limits of human knowledge and the relationship between subject and object, observer and observed. Drawing on Kant, he argued that we can never access the thing in itself, the noumenal reality beyond our perceptions. We only access phenomena, the world as it appears to us, through our methods of observation. The uncertainty principle formalizes this limitation within physics. It says that certain aspects of reality are forever beyond the reach of observation, not because we lack imagination or technology, but because the structure of nature forbids it. Some thinkers have gone further, suggesting that quantum mechanics reveals something profound about consciousness and reality. They argue that the participatory role of observation, even if not requiring human consciousness, suggests that reality is relational rather than absolute. The universe doesn't consist of isolated objects with intrinsic properties, but of relationships, interactions, measurements. What we call reality is the web of these relationships. This relational ontology challenges the classical picture of a world made of independent things, existing in space and time. Instead, things are what they do, what they interact with, what they measure and are measured by. This brings us to the measurement problem, one of the deepest puzzles in quantum mechanics. The mathematical formalism describes systems as evolving smoothly according to the Schrödinger equation, spreading out into superpositions of multiple states. But when we measure, we always get one definite result, not a superposition. Something seems to cause the wave function to collapse, to jump from many possibilities to one actuality. What causes this collapse? Is it a real physical process, or just an update of our knowledge? Different interpretations give different answers. The Copenhagen interpretation, which Heisenberg helped develop, says the collapse is real, but doesn't specify a mechanism. It treats measurement as fundamental and somewhat mysterious. Many worlds' interpretations deny collapse altogether, saying that all possible outcomes occur in branching parallel universes. Collapse theories propose physical mechanisms that randomly collapse wave functions based on mass or complexity. Bohmian mechanics eliminates collapse by introducing hidden variables and deterministic particle trajectories guided by a wave. Each interpretation has strengths and weaknesses, philosophical costs and benefits. What unites all these interpretations is the acknowledgement that Heisenberg's uncertainty principle is real, experimentally verified, and cannot be ignored. Countless experiments have tested the principle in increasingly precise ways. From measuring positions and momenta of particles, to time-energy relations in atomic decay, to sophisticated quantum optics experiments, the uncertainty principle holds. It's not a relic of early quantum confusion. It's a cornerstone of our best scientific description of nature. Technologies like electron microscopes, quantum cryptography, and quantum computing all depend on understanding and navigating quantum uncertainty. The practical implications of the uncertainty principle extend into unexpected domains. In engineering, it limits the precision of measurements at small scales. In chemistry and biology, it affects how electrons behave in atoms and molecules, shaping the structure of matter and life. In cosmology, quantum fluctuations in the early universe, governed by uncertainty relations, are thought to have seeded the large-scale structure of galaxies we see today. The principle isn't just abstract philosophy, it's woven into the fabric of physical reality at every scale. Yet, despite its ubiquity and experimental success, the uncertainty principle remains profoundly counterintuitive. Our brains evolved to navigate a macroscopic world where objects have definite positions and speeds, where seeing doesn't disturb, where knowledge accumulates without limit. The quantum world violates these intuitions at every turn. Accepting the uncertainty principle requires a radical shift in thinking, an acknowledgement that reality at its foundations is stranger than we imagined. This strangeness has cultural impacts beyond science. The uncertainty principle has been invoked, often incorrectly, in discussions of free will, consciousness, postmodern philosophy, and even spirituality. Some use it to argue that science admits uncertainty. Therefore, all knowledge is relative. Therefore, truth is subjective. This is a misunderstanding. The uncertainty principle is a precise mathematical statement about specific physical quantities. It doesn't license general epistemic chaos or subjective reality. It's a constraint on measurement, not a free pass for mysticism. Nonetheless, the principle does humble human knowledge in important ways. It reminds us that the universe is under no obligation to conform to our expectations or desires for certainty. It teaches that limits exist, not just in practice, but in principle. It shows that observation is not passive, but active, that we are participants in the reality we study, not detached spectators. These lessons, when understood properly, enrich rather than undermine science and philosophy. Heisenberg's discovery also sparked ongoing debates about realism, the idea that the world exists independently of our observations. Realists want to believe in an objective reality out there, with or without observers. But quantum mechanics, especially the uncertainty principle, makes certain forms of realism difficult to maintain. If particles don't have definite properties until measured, in what sense do they exist beforehand? Can we say an unmeasured electron has a position, even though we can't know it? Or do we have to accept that position simply doesn't exist as a property until measurement creates it? Bell's theorem, developed by physicist John Bell in 1964, deepened this crisis for realism. Bell showed that no local hidden variable theory, no attempt to restore classical determinism and objective reality, while respecting Einstein's relativity, could reproduce all the predictions of quantum mechanics. Experiments, testing. Bell's inequalities have overwhelmingly confirmed quantum mechanics and ruled out local hidden variables. This means we must give up either locality, the idea that distant events can't instantly affect each other, or realism, the idea that particles have definite properties independent of measurement. Either way, our intuitive picture of reality is shattered. Heisenberg was aware of these philosophical depths and engaged with them throughout his career. He corresponded with philosophers, wrote books exploring the implications of quantum mechanics for broader questions of knowledge and reality, and struggled to articulate what his principle meant for our understanding of nature. He saw science and philosophy as inseparable, not isolated domains. The uncertainty principle wasn't just a technical result in physics. It was a statement about the human condition, about the boundaries of knowledge, about the relationship between mind and world. In his later years, Heisenberg reflected on the harmony between science and faith, between rational inquiry and spiritual meaning. He didn't see the uncertainty principle as undermining order or purpose, but as revealing a deeper kind of order, one that includes indeterminacy, relationality, and emergence. The universe wasn't a dead machine, but a dynamic, evolving, participatory reality where observers and observed co-create the phenomena we study. This vision resonated with certain religious and philosophical traditions, though Heisenberg himself was careful not to conflate physics with theology. The legacy of Heisenberg's uncertainty principle continues to shape contemporary science and philosophy. Quantum information theory explores how uncertainty limits information storage and transmission. Quantum computing leverages superposition and uncertainty to perform calculations impossible for classical computers. Quantum cryptography uses the impossibility of measuring quantum states without disturbance to create unbreakable codes. These technologies turn Heisenberg's fundamental limit into practical advantage. Meanwhile, philosophical debates about consciousness, free will, and the nature of reality continue to invoke the uncertainty principle as evidence or inspiration. Neuroscientists discuss whether quantum effects in the brain could influence cognition. Philosophers of mind debate whether quantum indeterminacy provides room for mental causation. Ethicists consider whether quantum randomness affects moral responsibility. These discussions are often speculative and controversial, but they testify to the enduring impact of Heisenberg's insight. Ultimately, the uncertainty principle forces us to confront a humbling truth. We cannot know everything, not because we're limited or lazy, but because the universe itself prohibits complete knowledge. There are questions we cannot answer, measurements we cannot make, certainties we cannot achieve. This isn't defeat, it's enlightenment. It's recognition that reality is richer, stranger, and more mysterious than the clockwork universe of Laplace's demon. It's an invitation to embrace uncertainty, not as ignorance, but as a fundamental feature of existence. Werner Heisenberg proved your mind is wrong. If you thought knowledge could be absolute, observation could be passive, and reality could be fully grasped. His principle doesn't destroy science, it deepens it, revealing layers of complexity and wonder beneath the surface of classical physics. It challenges us to rethink what it means to know, to observe, to exist in a universe where certainty has limits, and where the boundary between observer and observed blurs in quantum foam. So the next time you look at the world and assume you know what you're seeing, remember Heisenberg. Remember that, at the deepest levels, particles dance in uncertainty. Properties flicker into existence under observation, and knowledge itself bends to the strange rules of quantum mechanics. You can't know everything. Nature won't allow it, and that might be the most important thing you'll ever learn. The universe doesn't owe you certainty. It offers you mystery instead. And in that mystery lies the true adventure of understanding.